Let's look at this scatter plot with histograms. So the primary goal here is help you to understand the relationship between a person's height and weight, which we try to formulating a mathematical model that can help us to predict weight based on height. Let's try to analyze this scatter plot. The dots represent individual data points, which show the weight and height of different individuals, and this horizontal line is trend line, which runs across scatter plot, which indicating the mean weight of all individuals, regardless its height. And this suggests an initial attempt to find a simple average, though it doesn't reflect any dependency of weight on height. Let's look at the top histograms, which is the height distribution, which shows how the heights are distributed among the individuals in this dataset. The beans represent the ranges of height, and the height of the bars indicates the frequency of individuals within those height ranges. Now, let's look at the right histogram, which is the weight distribution, which is similar to the top histogram, but this reflects how weights are distributed. It appears there is a range that contains the majority of these weights. So from this scatter plot, it is evident that there is no straightforward, linear, or easily discernible relationship between height and weight in this dataset, and the spread of the data points suggests highly variability, which indicates that the height alone may not be a sufficient predictor of weight, which align with the factor that maybe other factors like diet, lifestyle, or genetics also influence weight, right? So there's no clear pattern. So this example is excellent for illustrating the challenges in predicting an outcome based on a single feature when we have multiple influencing factors are involved. So it highlights the importance of considering a broader range of features and possibly more sophisticated modeling techniques, especially in real-world scenario where simple models might not capture all nuances of the data. Let's look at the second data set, which demonstrates a clear linear relationship between height and weight in contrast to our first data set, right? So this observed pattern, where the data points align closely around a straight line, suggests that the weight increases linearly as the height increases, so which allowing us for straightforward prediction of weight from height just by using this linear model. Let's talk about the reasons for these different patterns in the second data set. The first reason is the nature of data collection. So these data may come from different populations or subgroups. For example, the first data set could include a broader, more diverse population, while other factors besides height might significantly affect the weight. But the second data set may be more homogeneous or might have collected under condition that minimize the variation other than those caused by height. And the second reason is data integrity and scope. So variations in how the data were collected, like for example the measurement method and accuracy, can influence the pattern we observe here. So the scope of each dataset might differ. The first dataset may have a wide range of ages or includes more factors that may affect weight. And the third reason is the statistical properties. The second dataset shows the bimodal distribution in both weight and height histograms, which could suggest the presence of two distinct groups within the data, such as males and females, each with different average weights and heights. The Gaussian mixture suggests that each dataset might include mixed subpopulations like genders, and each following its own normal distribution for height and weight. So the mixture of two normal distribution means that the overall distribution of height or weight is the combination of the two different normal distribution, which is likely corresponding to different biological or demographic groups. Let's try to analyzing these subpopulations separately, which is for example males and females. We can obtain a clear and more accurate understanding of the relationship between the height and weight within each group. So this approach might reserve the variability which we see in the first data set. Let's try to visualize a graph where individuals are categorized by 5 levels of obesity They are plotted according to the height and weight. For each obesity category, this graph shows a linear dependency of weight on height. Let's try to categorize the obesity levels just by using different markers. So for each category, we can clearly distinguish them. So each obesity index, which is from 1 to 5, is represented by a different color. So the index 1 is underweight, which typically involves low weight ranges, as the index increases to index 5, which is extreme obesity. So the weight ranges increases significantly. And then we plot a trend line for each category to indicate the linear relationship. So for each obesity level, we have data points that reflect a realistic increase in weight with height, and each category have a different intercept to reflect the increased baseline weight, which is associated with the higher obesity levels. Let's talk about linear relationship. So for each obesity category, there is a distinct linear trend which is showing that within each category, the weight increases linearly with height. So this suggests that for people within the same obesity level, taller individuals tend to weight more. Each category demonstrates variability around the trend line, which is represented by the spread of data points. So this variability could be attributed to some other factors that are not captured in this model, such as muscle mass or body composition or metabolic differences. Let's try to interpret the implications. We have predictive insight, which is just by categorizing the individual by obesity level, we can make more accurate prediction about the weight based on height, as each subgroup follows a clearly linear trend. And the second is refinement in data exploration. Segregating data by relevant subcategories like the obesity index helps us in revealing hidden patterns that are otherwise subdued in a more heterogeneous dataset. So this can enhance both the analysis and the applicability of the data in real-world scenarios. This visualization can effectively demonstrate how the segregated data based on relevant characteristics like the obesity level can help us uncover more detailed and actionable insights. This graph depicts the linear relationship between height and weight, which can be formulated as weight equals omega 0 plus omega 1 times height, where the omega 0 and omega 1 are parameters that can be learned from the data. Omega 0 is the intercept, which represents the estimated weight when height is 0, although interpreting the intercept in this context doesn't have any practical real-world meaning, as the negative of 0 height isn't feasible, right? But it is crucial for fitting the model to the data. And also the omega 1 is the slope, which indicates that for each centimeter increase in height, the weight increases by omega 1 kilograms. In linear regression models, the primary task is to find the best values for these parameters omega 0 and omega 1 so that we can minimize the difference, which is the error, between the predicted weights and the actual weights in the dataset. So this process is known as fitting or training the model. So this is a simple example of predicting weight from height with just one feature, which is height, and a linear dependency that shows the fundamental concept behind more complex models. Although some deep learning maybe involve more intricate structure and maybe potentially millions of parameters, but the core idea remains similar, which is just adjusting the parameters to best capture a relationship between the input feature and the target output.